Welcome to Cambridge IGCSE Physics, Lesson 21.18. 1 Semaich, Convection Basics. This is core content for your physics qualification, focusing on how heat energy transfers through moving fluids. Let's examine our learning objectives for today. By the end of this lesson, you will be able to know convection is important in liquids. This means understanding how heat transfers through water and other liquid substances. No convection is important in gases. This covers heat transfer through air and other gaseous materials. Understand convection involves movement of fluid. This is the key principle that distinguishes convection from conduction and radiation. These objectives target Assessment Objective 1, which focuses on scientific knowledge and understanding. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, convection, which means heat transfer through fluid movement. This is different from conduction, which occurs through direct contact. Second, fluid, which means any substance that flows. This includes both liquids like water and gases like air. Third, convection current, which means the circular movement pattern that forms in heated fluid. Understanding these terms precisely is crucial for exam success. Let's explore our first core concept. What is convection? The fundamental principle states that convection transfers thermal energy through fluid movement. This means heat moves not by direct contact like conduction, but by the actual movement of the heated material itself. The definition is heat transfer method, where warmer, less dense fluid rises and cooler, denser fluid sinks. Key requirements include the fluid must be able to move freely. This is why convection doesn't occur in solids. Temperature difference creates density difference. Hot fluid becomes less dense. Gravity provides the driving force. It pulls denser cool fluid down. The diagram illustrates a complete convection current. Warm fluid rises on the left, flows across the top, cools and sinks on the right, then flows back along the bottom to complete the cycle. Now we examine convection in liquids. This follows Cambridge IGCSE practical requirements. Liquid examples include water, cooking oil, and liquid metals like mercury. The demonstration setup uses a beaker of water with a heat source underneath. We add potassium permanganate crystals as a tracer. These dissolve to create purple colouring that shows fluid movement. We observe purple trails that reveal the convection current pattern. Safety is paramount. Handle chemicals carefully and always use eye protection when working with potassium permanganate. The diagram shows the complete setup. The Bunsen burner heats water from below. The purple crystal dissolves, and its trail shows the circular convection current, rising near the heat source, flowing across the top, then sinking down the cooler sides. Convection also occurs in gases. Gas examples include air in our atmosphere, steam from boiling water, and other gases like carbon dioxide. The demonstration method uses a glass box with a candle inside for heating. An incense stick produces visible smoke that acts as a tracer to show air movement. We observe that smoke rises above the candle where air is heated, then flows across the top of the box and down the opposite side where air is cooler. This creates the same circular pattern we saw in liquids. The diagram shows hot air rising from the candle flame, flowing across the top, then sinking down the far side. Air enters through holes at the bottom to complete the circulation. This demonstrates that convection currents form in gases just as they do in liquids. Let's work through our first example. The problem states, explain why convection cannot occur in solids, but can occur in liquids and gases. We need to provide a scientific explanation using particle theory. Step 1. Consider particle arrangement. In solids, particles are held in fixed positions by strong intermolecular forces. Step 2. Examine liquid particles. In liquids, particles can move past each other freely while staying close together. Step 3. Analyze gas particles. In gases, particles move rapidly in all directions with large spaces between them. Step 4. Draw the conclusion. Convection needs particle movement to transfer heat energy from one place to another. The answer is, convection requires fluid movement. Solid particles cannot move from their fixed positions, preventing convection currents from forming. Liquid and gas particles can move freely, allowing convection currents to develop and transfer thermal energy. Example 2 examines convection current formation in detail. The problem asks us to describe how convection currents form in heated water. Let's analyse step by step. First, water near the heat source warms up. This increases the kinetic energy of water molecules. Second, warm water becomes less dense. Heating causes thermal expansion, making the same mass occupy more volume. Third, less dense water rises upward. Buoyancy forces push the lighter warm water up through the denser cool water above. Fourth, cool water sinks to replace it. Gravity pulls the denser cool water down to fill the space. The result is a circular flow pattern that continues as long as heating continues. The graph shows how temperature increases over time during heating, with the rate of increase slowing as convection becomes established and heat distribution becomes more uniform. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, name 2 types of fluid where convection can occur. Think about the definition of fluid and the examples we've discussed. Question 2 is intermediate. It states, explain why hot air rises during convection. This requires you to apply the concepts of density and buoyancy we've learned. Question 3 is advanced. The question is, describe how you would demonstrate convection in water using a tracer. This tests your understanding of experimental methods and observation techniques. For all questions, remember to show you're working clearly, include units where appropriate, and check your answers make physical sense. Write your answers now before looking at the solutions. Physics principles power our modern world. Let's see how convection applies in practice. In weather systems, atmospheric convection creates wind patterns and storms. Warm air rises from heated ground, creating low-pressure areas that draw in cooler air. In home heating, radiators use convection to warm rooms efficiently. They heat air, which rises and circulates throughout the room. In cooking, ovens use fan-assisted convection to circulate hot air for even heating of food. These applications show why understanding convection matters. Career-wise, convection knowledge leads to meteorology for weather prediction, HVAC engineering for heating, ventilation and air conditioning systems, and thermal design for industrial processes. The concepts you learn today become tomorrow's solutions for climate control, weather forecasting, and energy-efficient heating systems. Let's review the solutions. For question 1, the answer is liquids and gases. Specific examples include water and air, oil and steam, or any other fluid substances. This is correct because fluids can flow and move freely. For question 2, hot air rises because heating causes air to expand, making it less dense than the surrounding cool air. Buoyancy forces then cause the less dense hot air to rise upward through the denser cool air. For question 3, the demonstration involves heating water from below using a Bunsen burner, adding potassium permanganate crystals as a tracer, then observing the purple trails that show the circular convection current pattern. Exam success tips. Always use key scientific terms like density, buoyancy, and fluid movement. Describe complete convection cycles showing rising, horizontal flow, and sinking phases. Link explanations to particle theory by mentioning molecular motion and spacing changes. Draw clear diagrams with arrows showing flow direction and label all components clearly. Let's summarize today's lesson. The key points to remember are: first, convection is heat transfer through fluid movement in circular currents. This distinguishes it from conduction and radiation, as it requires actual movement of the heated material. Second, fluids including liquids and gases allow convection due to particle mobility. Solid particles cannot move freely, so convection cannot occur in solids. Third, the mechanism involves density differences that drive rising and sinking motion. Heating reduces density, causing upward movement. Cooling increases density, causing downward movement. These 3 concepts form the foundation for understanding thermal energy transfer. For further study, review the convection demonstrations we discussed and practice explaining the observations. Connect convection to particle theory by explaining how molecular behavior changes with temperature. The next lesson covers radiation heat transfer, which completes our study of the 3 heat transfer methods. Ensure you understand convection thoroughly, as it connects to weather systems, heating technology, and many engineering applications.